5 talks in this session. The first talk is by Yang Liu, who will talk about sparsifying sums of norms.
Yeah.
And it's
Thanks,
a boat talk.
Yeah. Thanks, Venkat, for the introduction. I'm Yang. I guess I'll just write my name. And I just graduated from Stanford, and after this workshop, I'll be at the IAS for a postdoc for about a year and a half. So now let me talk about sparsifying sums of norms. The sparsification problem in general is the following. We have functions, f1, fn, and they're functions on Rd, mapping to Rd0. And let's define the sum, f of x, f1x plus fnx. And the sparsification question is in general, can we reduce the number of terms in the sum in some way while still maintaining the value of the sum up to some approximation factors? So formally, we can ask what is sparsification mean? We want to find some weights, w1 to wn, and a lot of them are going to be 0. That's kind of the goal. These weights are non-negative weights. And if we define f tilde of x to be w1 f1x plus wn fnx, the goal is to ensure that f of x minus f tilde of x is in most epsilon times f of x for all x in Rd. And the second property is that at most, some number of w1 to wn are non-zero. I guess in a lot of sparsification problems, the question is what's the best thing you can put here? And very optimistically, the dream is something like epsilon to the minus 2 times d, and then let's say some logarithmic factors in d over epsilon. So that's kind of the dream goal. Now, in general, sparsification has led to, or like understanding the settings, which functions you can sparsify, has led to a lot of progress in fast algorithms for convex optimization, graph theory, etc. Let me just give some examples. One very classical example is when you have vectors a1 through an in Rd, and the function fi of x is defined as ai dot x squared. In that case, this is known as spectral sparsification. And it's basically akin to maintaining the form induced by the matrix, which is, let's just write it like x equals a1 transpose. You want to sparsify that sum. And that's called the spectral sparsification problem. Okay. I guess what I'm going to tell you about is a result I've been working on recently that tries to understand maybe in more generality what functions you can sparsify. I'll just say one version. We can show a lot of things, but I'll just state one particular version. Sums of norms. So hopefully this is clear. I'm going to let fi of x be ni of x, where ni is a semi-norm on Rd. And then in this case, the theorem is that there exists weights w1 to wn that make it a sparsifier, that make n tilde x w1 n1x plus wn n sub n of x, and epsilon sparsifier, in other words, satisfies that condition over there with the epsilon. And the number that are non-zero is at most, I guess, epsilon to the minus 2d, then something like log to the 3.5d over. Okay, so that's like that's a theorem. Okay. I guess the reason this is, in some sense, it seems quite general, and in some sense generalizes this because ai dot x is a norm. Obviously, I would need to have like squares here or something, but something like that. Okay, so that's the theorem statement, and it's quite general. There's applications, for example, to sparsifying sums of symmetric submodular functions. This is because you can show that the Lovász extension of a symmetric submodular function is indeed a semi-norm. So, for example, you can get things on that. Okay.
I guess semi-norm means non-zero things can have zero norm.
Oh, that's right. Yeah. So like it satisfies the triangle inequality basically and scaling, but okay. And I will just state the algorithm and then I'll conclude. In general, for sparsification, all the algorithms take the following form. We will pick real numbers P1 to Pn that are at least 0. And then the way we construct the sparsifier is we set, I guess also they're probably also in most 1. The way you construct the sparsifier is you set Wi to be Pi inverse with probability Pi and 0 otherwise. This way, the sum there is unbiased at least. The expectation of Wi and I of x is going to be Ni of x. So the sum is unbiased, but obviously you need to show it holds for all x, which is the difficulty. So I guess I'm just going to state how we choose the PIXs and kind of just end there. So the way we choose the PIXs to construct the sparsifier is we define the measure mu, which is proportional to e to the minus n of x, where n is the sum. And this is a log concave distribution. And then we use and then we set Pi to be rho times the expectation of x from mu of Ni of x. And rho is going to be this like an oversampling parameter, epsilon to the minus 2 log to the 3.5 d over epsilon. So yeah, if you pick these PIs defined this way and you sample, then we can show that it is a sparsifier with high probability. Okay, so I'm just gonna conclude there.
Questions?
Yeah, any connections to learning or regression?
Any connections to learning or regression? Good. That's a good question. To answer that, there's a lot of regression problems. For example, let's consider the problem of LP norm regression. I'm just going to write it here. The problem of LP norm regression is the following. It's you want to minimize the sum over I of the absolute value ai dot x to the p. Right? So if you want, for example, a 1 plus epsilon approximate solution of this, you would sparsify. This where the function f of I is this. Okay. Now that will give you a 1 plus epsilon, which is like a low accuracy solution. It turns out that if you want high accuracy solutions, you need to sparsify not this term, but actually things that are more complicated. For example, these things that are like, I don't know if you've heard of like Huber losses, but they're basically functions that go beyond this. And if you understand sparsification for that, then you can get fast algorithms for high accuracy regression and things like that.
One more question.
Can you compute those probabilities efficiently?
So because you can sample, depends on what efficiently means. In polynomial time, yes, but not much more efficient than that. Like if you assume an access to like an oracle for n of x, then you can get these probabilities well enough to high accuracy. Not high accuracy, it's low accuracy.
And it looks like this is equal to the effective resistance in the spectral sparsification case.
Correct.
Is it also equal to is there a sparsification version of
good.
this?
So when this fi of x is the squared, it equals the effective resistance. But I guess for any other functions, it will give, I guess, different sampling probabilities, which also give a sparsifier up to polylog factors. But they should be different from Lewis weights. Yeah.
Okay, Siddharth, maybe Hui can set up.
Yeah.
Can you say anything when the domain of these functions is not RD and say something like the hypercube?
So I guess, can I say anything in that case? So for example, as I was saying, this result captures the case where like fi of x are symmetric submodular functions, which are naturally only defined in the hypercube. but they have an extension to RD, which is a semi-norm. So like, for example, you might attempt to do things like that. Yeah.
Cool, cool.
Obviously, happy to take questions afterwards.
Thank you. Okay, next we have Pham, also from Stanford, who will tell us about random graphs, thresholds, and additive combinatorics.
So Pham, I'm finishing up my PhD at Stanford. I'll be here over the summer, and then next year I'll still be local at Stanford. So today I hope to tell you about some stories about various models of random graphs, and recent progress in random graphs has seen quite a few fruitful connections to other surprising areas. I won't touch so much on the connection to probability theory and stochastic processes today, but I'll focus a little bit more on some interesting connections to additive combinatorics. So let's start with the random graph models that we are interested in. So first we have the classical model of Eddy-Shreni random graphs. So in this case, your edges would just be independent Bernoullis with probability P. Then we will also consider random Cayley graphs, and there are natural motivations for this. So to define a random Cayley graph, we would first fix an ambient group G. So to us, G is an arbitrary finite group. And the Cayley graph is specified by a generating set S, which is a symmetric subset of G. And by symmetric, I just mean that if you have an element G in S, then G inverse also have to be in S. And then we would define a graph where we put an edge between two elements of the group X and Y if X, Y inverse is an element of the set S. Okay, this would define an undirected graph. And now if you want to define a random Cayley graph, you can just put elements in the generating set S independently with probability P subject to the symmetry condition. And in that case, you would get this random Cayley graph, GP. Okay, so again, as typical in the case of random graphs, we are interested in finding structures in either the Eddy-Shreni random graphs or these random Cayley graphs. So in other words, we are usually interested in monotone properties that are defined on these families of random graphs. So to give some motivation, let me revisit one of the first applications of the random graph, and that's to Ramses theory. And in this case, we are interested in studying a distribution of large independent sets or large cliques in random graph. In the Eddy-Shreni case, this is very easy. So just by the vanilla first and second moment method, we can prove that, let's say in the dense case, so when the density P is equal to 1/2, the largest independent set, and similarly the largest clique, will have size about 2 plus 0 of 1 times log base 2 of n. And in fact, we know much more precisely just based on the second moment method. For example, this independence number is going to be typically just take on one of two values and actually on just a single value for most values of n. So let's see what would happen in the random Cayley case. And now we see that we seem to run into quite a lot of trouble. So even if we just want to compute the first moment of the number of independent sets in random Cayley graph, we see that we run into quite non-trivial additive combinatorial or group theoretic question. And in particular, the question here is how to count the number of subsets A of the group G for which the product sets A times A inverse have a small size. And it's not so clear how to do this. There are several nice works by Ben Green and Robert Morris, where they rely on additive combinatorial arguments or harmonic analysis to prove to get these counts, and in particular obtain the first moment. So they give some bounds on the size of independent sets in random Cayley graph. But because it relies heavily on the additive combinatorial inputs, it only works for very special groups, such as F2 to the n or the cyclic group Zn. And even just in these cases, we already see that the answer can depend quite heavily on the group structure. So in Zn, the clique or independence number will be similar to the Eddy-Shreni random graph. But in F2 to the n, the size of the largest clique and independent set is asymptotically larger. So it's about order log the size of the group times log the size of the group. So we're trying to move beyond the case of this very special, nice abelian group. And so we try to seek some more robust combinatorial argument. And in upcoming work with David Collin, Jacob Fox, and Liana Yepremian, we can prove that indeed the independence and clique number of a random Cayley graph of density 1/2 in an arbitrary group G, not necessarily abelian, is always bounded above by log size of G times log size of G. And as we mentioned before, this is actually tight, for example, for any finite field vector space over a field of bounded characteristic. And as I mentioned, our argument avoids using sophisticated additive combinatorics. So it's just a purely probabilistic argument and just purely combinatorial. So in particular, the argument also vice versa implies strong corollaries on the word of additive combinatorics. So it implies strong bound on counts of sets with small product sets in general groups. And the argument actually also works for a family of graphs that are much more general than just a random Cayley graph. So we call these entangled graphs. And they actually have also appeared before. And so here there are several interesting questions to ask. So, well, for a general group G, we saw that we may not be able to hope that the random graph would be Ramsey. And by being Ramsey, meaning that it have independence and clique number big O of log the size of the group. And we may be interested in seeing how to remove this log factor. And we have partial progress on this in several cases. So we can define a tweak of the random model for which even over finite field vector spaces, we can define a random Cayley graph, not a uniformly random Cayley graph, that satisfies the Ramsey property. So it has small independent sets and cliques. And furthermore, so through these arguments, we can construct self-complementary Ramsey graph, which answers some question of Alon that was posed based on some connection between self-complementary Ramsey graph to dual source coding and repeated communications. And the other motivation here is on Alon's conjecture, Alon conjectures that in every group G, there is a Ramsey Cayley graph with small clique and independence number. And we can prove Alon's conjecture for a wide range of groups, although not all of the groups yet. So one of the last important open cases would be the case of over F2 to the n. Okay, so far the entire discussion is just about cliques, and and usually in random graphs, you want to study much more general things than just cliques. So let's just take a little bit of a broader view now. So in random graph, we usually try to study thresholds, and given a desired family of structures like cliques or cycles, the threshold is the transition point at which the random graph transitions from unlikely containing to likely containing that structure. And this recent result I have with Jin Young Park, building on previous beautiful breakthroughs on the sunflower conjecture, fractional Kankrai conjecture, and also our joint work on telegram selective process conjecture, essentially give you a reduction between the probabilistic task of estimating the threshold to a combinatorial task of estimating the expectation threshold, which I will not define, but it is kind of a linear program, or in other words, kind of a deterministic but complex combinatorial object. So, well, this theorem is nice, but the point of having this theorem is that we want to be able to apply it, but then we realize that out of just a few highly specialized, although challenging cases, estimating the expectation threshold is actually can be very challenging. Towards this task, I'll just mention here two of my recent work with my co-authors that kind of show that this task can be quite interesting in itself, and it draws on quite a lot of tools in combinatorics and theoretical computer science and algorithmic ideas. But there are also many other recent works along this line by other respected researchers. And in fact, if we revisit our previous discussion of random Cayley graph, we see that, well, this theorem actually holds much more generally, not just to random graphs, but also to general monotone Boolean functions. So in particular, it also holds for the random Cayley graph. But the main difficulty in the Cayley case is that we actually don't have a very good technique of understanding the expectation threshold for the family of random Cayley graphs. So with that, let me end with some interesting things that we can try to do next. So for example, we can try to build more general and robust techniques for estimating expectation thresholds. But specifically to random Cayley graph, we may also try to have a much more general toolbox to understand thresholds and properties of sparse random Cayley graphs. And I haven't mentioned this, but in quite a lot of basic properties, like in the large independent sets or containment of Hamiltonian cycles, the Cayley case have been mostly attacked by going through the spectral method or by using the spectral bound. So in other words, so far we are finding structures in random Cayley graph just by using the fact that they are pretty good spectral expanders. But these will lead to quite suboptimal bounds, and it's quite an interesting task, but also challenging to try to use fully the randomness of these random Cayley models and go beyond the bounds that are given by the spectral techniques. Okay, thank you.
Any questions for Hui?
So your result works for any group, but I guess I found that surprising because sometimes there's groups which are very different from finite field vector space, like if you have a quasi-random group or something. So do you have an explanation for this, for why they should be the same, even though the groups tend to have very different?
Yeah, so the bound that we prove here is just an upper bound on the clique and independence number. So this upper bound turns out to be tight for finite field vector spaces, but most of the time it will not be tight. So for most groups, you expect that this is actually just big O of log G. So like in the case of cyclic groups, it's big O of log G. So this is not a theta, it's just a big O. And the group structure would come to tell you where between log G and log G times log G, the clique and independence number will be.
So for like a highly non-abelian group, would it be closer to log G?
Yeah, so one would expect that in a highly non-abelian group, the answer should be closer to log G. It's more likely Ramses. And this log G, I can also tell you that it roughly comes from the fact that there are many, many subgroups, like let's say in a finite few vector spaces. And so unless your group have this strange property that there's a whole ton of subgroups at the appropriate size, then the answer will not suffer from this additional log factor.
Any other question? So I had a quick question. Do you think any of these would be easier to de-randomize than GN1/2? Because I mean, explicit constructions of Ramsey graphs is sort of been a major focus.
Right. So they certainly use a lot less randomness, or the random Cayley model. There's only linear set of quadratic amount of randomness, but it's not clear at all if it's easy to just fully de-randomize that. Yeah. That was one of the first motivation for us looking at this random Cayley model.
Right. So no further question. Thank you. So we'll close off the program with 3 talks on influences in Boolean functions and related topics. So the first of those will be given by Makrand on something about block-multilinear functions.
You will see.
You will say, okay.
Did it for a reason. Yeah, so I tried to use ChatGPT to write some jokes for this talk, but your sense of humor is worse than mine, so you'll have to suffer. Okay. So in the following this event, so you're supposed to meet me. So this is who I am. I've been a postdoc here for the last almost 2 years. So if you want any recommendations about any coffee shops, breweries, hikes, or if you're craving for danger, just talk to me. And my time here is coming to an end. I'm moving to UFI at the end of summer. And broadly, I'm sort of interested in complexity, different aspects. And recently, I've been thinking a lot about quantum complexity. Also worked on optimization and stochastic processes. So, yes, I'm supposed to give a talk. So let me tell you a short story about polynomials and decision trees in the next 5 minutes. So let's meet the first protagonist of the story, which is a polynomial. We'll consider multivariate polynomials in n variables. And we'll assume that the polynomial is like multilinear, so there are no squares or higher powers of any monomial. And we're interested in the values of this polynomial on the vertices of the hypercube on all plus minus 1 to the n points. And for this talk, we'll assume that polynomial is bounded. So it takes values between 0 and 1 and different values on different points of the cube. So I guess that's the first protagonist. Let's meet the second protagonist, which is a decision tree. Probably lives in a different universe from this partition. So I mean, here you query like a bit. And depending on the value of the bit, you choose another bit to query. So this gives you algorithm to compute the value of a function on any polynomial. And when you reach a leaf of this decision tree, you just output whatever number is written there, and the number written is between 0 and 1. Okay. So if this decision tree has depth d, it should be very easy to see that you can write whatever the function this computes as a polynomial of degree d, just by doing some sort of recursion. And the main question that I've been thinking about for the last few years is, can you go the other way? If you have a degree D polynomial that is bounded on the hypercube, can you construct a decision tree for it that's okay, maybe allow you to blow up the size by a little bit, and I will also allow you to error on some fraction of the points. So you can be wrong on few fraction of the points if you want, or you can be close in, let's say, L2 or something. So that's the question. Seems very basic, but we don't know much about it. So let's look at a very simple case. So suppose the polynomial on most points of the hypercube is close to some constant value. Here, let's say it's close to 1/2. Takes, and maybe there are a few points where it's very far away, like 0. In this case, there's a very simple decision tree for it. You just output 1/2 at the leaf. So it's very easy to construct a decision tree for this case. But what happens if the polynomial is varying a lot? So sometimes it takes value 0, sometimes it takes very large values all over the cube. So can you build a decision tree for it? And this is where this conjecture of ends and unbiased comes in. It's a sort of very well-known conjecture. Probably people here know more about it than I do. So this basically says that there is some coordinate direction, so some axis parallel direction, along which the derivative of this polynomial is very large on average. Meaning that if you go from left to right in this picture, the value of the polynomial changes a lot on average. Okay, it changes by 1 over polynomial in the degree. So if we have, if this conjecture is true, if there is always such a direct coordinate direction for every polynomial that is bounded, then you can very easily construct a decision tree by doing some sort of recursion. So, I mean, if you query this variable, you split the cube into 2 parts, and I mean, it's fairly easy to show that each time you do this, the variance of the polynomial goes down. It starts varying less and less, and at some point you're back in the previous case where the polynomial is basically constant. So, and since the influence is 1 over poly d, you only need to take poly d queries basically. Okay, any questions? Yes, I'm not supposed to ask questions, but okay, let me continue. So one of the very interesting special case, or sort of a case that has an interesting application, is when this polynomial comes from a quantum query algorithm. So such algorithms, instead of querying bits, they can query input bits in a superposition. And for now, you don't need to know much about them. But if you can prove that there is a decision tree for even such polynomials, it will give you like a classical way to simulate any quantum algorithm that's efficient on essentially most inputs. That's a very interesting open problem. It's been studied for a while. So I guess I messed up the animations here, so this should come later. But so in a recent work, we studied like a special case. So let's look at the polynomial with sort of every monomial contains variables, one variable x, another variable y, another variable of the form z. So the variables are partitioned basically, and each monomial is built out of such variables. So even if you have such polynomials, again, this conjecture is wide open. We don't know much about it, although there is some work. And what we looked at in a recent work, this very nice observation that was made by Arunachalam, Brieth, and Paluzelos, it says that if this polynomial actually comes from a quantum algorithm, it's not just bounded into the hypercube, but it has a much more nicer property that is completely bounded. And let me just tell you on a high level what it means. It means that if you view this polynomial as a matrix polynomial, your x1, y2, z3 are just matrices now of some arbitrary large dimension. And if you plug in matrices with operator norm at most 1, then the operator norm of this matrix polynomial as matrix still remains at most 1. So if you plug in scalars, this is exactly, and between plus minus 1, this is exactly the value of the polynomial in the hypercube. But now you're allowed to plug in matrices of larger and larger dimensions. And such polynomials sort of come out of quantum algorithms.
Do they have to be projections?
I mean, they can be unitaries. Operator norm at most 1. Yeah.
What about like they don't commute? So
I mean, okay, so that's why I wrote the polynomial in this form: x1, y1, z3. So there, everything orders basically fixed, and there they commute. If it's a normal polynomial, then I think you need to define what this norm is a little bit differently. So in a recent work, we sort of showed that in this case, this conjecture is true. And the coolest part for me about that, this relies on connections. It was called non-commutative probability or free probability theory. C-star algebra. So it's a very nice, very cool field. And this gives you a way to classically simulate some kind of quantum algorithms. Okay. So I think that's more or less it. I wanted to have like this animation, like the end of a movie where the credits roll, but my animation skills are, not strong enough for that. But this wouldn't be possible without all these wonderful works and wonderful ideas. So I guess, yeah, I have to give where credit is due. So thank you. And I guess, yeah, if there are more questions.
So if instead of completely bounded, you say it's bounded on matrices of dimension up to some n, do you get some bound depending on n?
We don't know how to prove that. What I would really like to prove if you plug in 2 by 2 matrices, or let's say even complex numbers, you can prove something, but we don't know how to prove. So for this proof, we really plug in matrices of like infinite dimension. You take n to infinity, and then it becomes like free operators and some C-star algebra. So it becomes much easier. Yeah.
For the answer and minus, you're just saying like the ith influence is one point. Okay.
Yeah.
And you care about this poly, right? If it was e to the minus d, that would just be followed by KKL.
Yeah, e to the minus d. It's not KKL. You need like some this d would free good Kelman would all. It's a bounded function. It's not a Boolean function.
Oh, gotcha. So the recent result you mentioned, like, it doesn't imply the answer and minus, right?
Only for these special completely bounded elements of this form.
Oh, okay.
Yeah.
So one question I have is, we now know the quantum to, randomized or deterministic query complexity, the relations, right? The polynomial relations. So how does errors and number n still fit in?
Yeah, those are like, you want to be really correct on all points. And if you ignore some fractional points, for instance, then we don't know.
Any other question?
Okay. Thanks for that. Oh, and I have to make a public service announcement for the fellows happy hour. You should show up because it's a lot of fun. And I guess Venkat will tell you more about it.
Yeah. Thanks for the plug. Okay, so we continue with more stuff on influence. Paivu will tell us about, I guess, this theorem with which one of the coolest names, in my opinion. It ain't over till it's over.
Hello.
Okay, so in this talk, I want to like share you with this result in over till it's over. It's actually, as already told, it's about the influences on Boolean functions. Okay, so maybe let me just review some basic definitions. So first, here we are interested in Boolean functions, and the influences for a variable xi with respect to this function is just the probability that you flip the value of a function by flipping your input xi on a uniformly random input x. And the max influence of this function is just the maximum over all the individual influences. Okay, so let's look at some examples. It's basic, but it's related for our results. So maybe it's good to look at 2 examples. The first one is the majority function. The majority function just outputs the majority bit of your inputs. And its max influence is order of 1 over square root of n. And this is because that if your input is sensitive, meaning that by flipping this bit, you flip the value of a function, it has to be the case that on your input, there are about equal number of zeros and ones, right? And on a random input, this event happens with probability like 1 over square root of n. And conditioning on this event, you have like the constant fraction of the majority bit, which you can flip. So that's why the majority function has max influence 1 over square root of n. Okay, that's the first example. And the second example is the tribes function adapts to AC0 circuits. And the parameters are chosen so that it outputs 0 and 1 with approximately equal probability. In particular, you were set defining for the n function as n over log n, and defining to the OR function as about log n. And the max influence for the tribes function is log n over n. Also, like, it's very easy to check why this is the case. Let's just consider the case where we have an input that outputs 0. So it can be calculated that with a constant probability, there will be a special OR gadget that outputs 0, and all the other OR gadget outputs 1. And in this case, the input to this OR gadget will be sensitive. You can flip them to flip the value of your function, and the other inputs you can't flip. They are not sensitive. So therefore, because depending to the OR gate is about log n, so the max influence of tribes function is log n over n. So for both these functions, their max influence is like polynomially small, and the output like 0 and 1 with about equal probability. And that's the kind of functions that we are being interested. Although it may be a little bit weird if you haven't encountered such functions before, but they actually appeared very naturally in many applications. Like the first application is the social choice theory, which is also like it n over till it's over name comes from. So for example, maybe after this meeting and during the weekends we want to hang out with our friends, and we want to decide whether we stay at home playing some games or enjoy some outdoor activities. And you really want to hang out together with your friends, so you need to make a decision. So maybe you will take the majority vote, or like you can use some other more complicated function to aggregate your decisions, like how we elect the president. But normally we always want some kind of criterion on how we actually aggregate this decision. So we don't want there is a single person that can kind of decide what's the outcome without caring about the other people's opinion. So max influences kind of captures this notion. And well, we are computer scientists, so more familiar things to us is the hardness of approximations. So we know the dictatorship test. And then third motivation maybe comes from this invariance principle phenomenon. Yes. So it loosely speaking, it says that if for your function there is no input bit that has a large influences, then you can actually replace this bit, if you consider it as a random Boolean variable, then replace it with a random Gaussian variable, and the output behavior will be similar. And probably the most like familiar example for us is the central limit theorem, when we add up a bunch of +1 -1 variables, then it's like to add up some Gaussian variables. Okay. So another notion that is probably very familiar to all of us is the random restriction. So we just want to say fix a p fraction of random variables by assigning uniform random values. Okay, so that's like the setup. Now I can really actually tell you what is about this it over till it's over theorem. So in this work, we actually we actually strengthened, we obtained an optimal version of this theorem. So in particular, we show that if we have a function of that has more influences and it's kind of balanced, it outputs 0 and 1 with approximately same probability, then we can set the Lie probability to be like 1 over log 1 over the max influence. Think about majority or the Travis function. That is, you keep only 1 over log n fraction of the inputs alive. Then with high probability that your function is not gonna be a constant function. So that's the result. Maybe let me make some remarks about this result. So this is optimal with respect to the alive probability because just consider the Travis function. It's depth 2 AC0 circuits, so by Hastad-Switch lemma, if you restrict 1 over log n fraction of your inputs, then it's gonna be a constant function with high probability. So that's the first part. The second part is like here, I just write it as being non-constant, but you can actually have yes, more quantitative version, like bound its how the variance changes under the random restriction. So we got some bound for that, and it will be optimal with respect to the majority function. You can analyze what happens for the majority function, and the two bounds were matched. Yeah. So so maybe more remarks. So the conjecture was first. The conjecture is just about suppose we keep like only we just restrict only a constant fraction of the inputs, then whether the remaining function is non-constant. And of course, we got something much stronger. And also, the original version was first proved by Morse O'Donnell and Leskowitz using invariance principle. Our approach is more like pathwise stochastic analysis. Okay, and also like Kohler, Lipschitz, and also they obtained a different approach. That's very nice, I think. Okay, yeah, so that's it. It's over. Thank you.
Any questions to open this question again, saying it's not fully over?
I'm curious. I remember that the original proof went through proxy analysis of the noise operator. Do you guys directly analyze restrictions, or do you also go through some?
Okay. We go through the restrictions. We directly analyze the restrictions. Yes, but I mean restrictions. You can also view it as a noise operator if you want. Yeah.
Other questions? Okay, thank you. Okay, for our final talk of the morning, we'll have Esty Kelman tell us about another famous conjecture in Boolean function analysis, the Fourier entropy influence conjecture.
So I thought that you should meet me and hear about influences, but you already hear about influences, but you didn't meet me. So I will tell you a little bit about myself, just because I have this slide and no one did, but okay. So I'm doing now a postdoc in Boston University and MIT. This is part of FODSI program, and I have many hosts. You can read the names by yourself. Last year I did postdoc in Israel, hosted by Gil Kalai, and we published a paper without Gil, with other people, about low degree testing over the reals, which is very interesting, but I'm not going to tell you anything about it today. Last year, I also visited here for the program of causality, and I really like to be here, so I came again. And I also contributed to the fraction of women in theoretical computer science, bringing my new daughter that today she has birthday. She's 1 year old. Her name Annette. And previously I finished my PhD that actually it felt like the previous talk was about the introduction for my PhD. So somehow, so I'm going to skip what is Boolean functions and the same cube that already appeared here. And I just like to see it like to coloring, and then we have the influential edges, which we already talked about them, just to see them here. So the influential edges just gone from two different values, and the total influence defined to be just the number of all of these influential edges up to some normalization. And this is very important parameter of Boolean functions. And if it's small, we are very interested in what's the structure of this. If it's large, we're also interested, but we don't know to say anything, essentially. And the famous first result, I think that established the Fourier analysis is the KKL, which says that there is a one variable with non-trivial influence. So we need the individual influences, which we just look for some direction and see how many influential edges we have in this direction. And the total influence is just the sum of all the influences. And then we can rephrase KKL as there is some variable, some direction with non-trivial individual influence, which is at least exponentially in the total influence. You can see that if the total influence is much smaller than log n, then this is not trivial. Okay, and then came the Fourier entropy influence conjecture, the famous conjecture that said that if the total influence is small, then the function is actually very close to sparse function. And then thanks to collaboration with Noam and others, we proved something very close to the Fourier entropy influence conjecture, which shows instead of concentrating on to the influence, we have here the other log. And this implies many things, sharp threshold and others. And one thing that I want to mention today is that functions with small influence are now can be agnostically learnable in very fast. So if we can think about k as log n over log n, then we have polynomial time agnostic learning. A bit about the proof. So in the proof, we show it's actually combined from correlation inequalities. I will say in a minute what is it. And it starts with proving the KKL theorem in a very basic proof and just improve it. When we apply random restrictions, and I will say what is it. So for correlation inequalities, we need the fact that every function has unique representation, the Fourier representation, and the degree is the Fourier degree, which the maximal degree. What do you think about it? And why are we interested in low degree functions? So one thing we can see that functions with small total influence actually close to small degree. And we know something about low degree functions, even not a lot. Actually, we know some things about Boolean functions with small degree. So at least we know the hypercontractivity, which is appears in many proofs. And what is a correlation? So just the inner product between two functions is a correlation between them, and this defines also L2 norm. I'm not sure why I say this, but okay. So the first lemma is something quite general, not really. So we have two functions. One of them is Boolean. The other one is not necessarily Boolean, but of low degree. And we want to say that if the influences are bounded, we actually can take this delta to be just the max influence that we saw. Then their correlation is bounded, some exponential in D, and the max influence, and something that's called cross total influence, which is just as the total influence of some function, but you use the two functions here. So the proof is easy, but I'm not sure today. And this actually implies the KKL. So it's quite easy to see that if we take just D to be twice the total influence, or 1 over epsilon, and G to be just the truncated F up to D, and we take now the correlation between F and its truncated degree, then using this bound, we just get the KKL. So this is just the first step. Now the question is, can we do better? And the answer is yes. Otherwise, we won't have say anything of this. And the way to do better is to refine a bit the analysis using the sizes of the influences. We use also generalize the influences. And the main tool is to reduce the degree using random restrictions. And we do it repeatedly until we get a good result. And we don't know how to continue to get the log, to get rid of the log. And I will talk more about it in the bootcamp. So if you're interested, you're invited on Monday. Do we have more time? Yeah, okay. So I'll just talk a bit about other questions that I wrote about on, if someone interested to know what I do, then talk to me. So another thing that I'm interested in are testing, property testing and estimation of properties of Boolean functions, and specifically complexities that might, that results might imply explainable machine learning. And another regime is delegating queries to untrusted sources in a way to improve sublinear algorithms and make them much faster using powerful, maybe untrusted server. And low degree testing in various settings is very interesting, and also Boolean and drills. And thank you.
Any questions?
If you have questions later, just on Monday.
I might have a quick question. So
Okay.
KKL is usually stated slightly differently, right? That there is a log n by n influential thing. This is equivalent to that form?
Yeah, it's actually implied from this form. That's
So
what they prove this.
I see. And this implies the other form. Okay.
Yeah, so why should we care about the Fourier entropy influence conjecture? Does it have any applications?
In terms of applications?
No. Why should I? So I understand that some people we care about ask the question, but why should I care about it?
I don't know. You should think about it yourself. I don't know why you do, or do you?
Would it imply something that maybe I am interested in?
I guess you should.
Thresholds for graph properties. So if you get it, you get that the total influence of graph properties is at least log n squared instead of log n, and then you get the sharp threshold. It's sharp for clicks.
And it seemed it will have some learning application too, this agnostic learning, but that you're able to get anyway bypassing the full conjecture. Is that what you said? The agnostic learning of functions with low total influence.
I'm not sure what you asked.
No. I mean, that doesn't matter.
This
Yeah.
gets up to like log n over log n, but the full conjecture would get log n.
Log n,
Okay,
yeah.
okay. But this almost gets there, bypassing the full conjecture. That was my
Yeah.
question.
It will help you also learn DNS.
Okay, any other questions? If not, thank you very much, Esty, and indeed all the speakers of this morning for a really good session. And thanks to the audience for coming and making the event a success. And that concludes this morning's program. And just a reminder for those who are part of the analysis and TCS summer program, there is an orientation this afternoon starting at 2 p.m. I guess in the room on the other side, 116. So, okay, thank you and have a great summer.